Hey, what's going on, guys? Welcome back to another stream here on the Mastery channel. Um, Today the plan is very simple. We're going to be grinding physics and maths, but first physics, mechanics 1, all of mechanics, all of electricity and modern. We need to try and get that all done, hopefully, and then do maths. I want to get financial maths, sequences and series, and proof by induction done. It's a lot to ask, but it's possible. But we're gonna have to start now. So best of luck, and I'm just gonna go through it. I think we'll start off with mechanics 2, and we'll make our way up. And we'll do some past papers as well, of course. So first and foremost, when we talk about mechanics, right? When we talk about mechanics, we need to talk about a formula. We need to talk about pressure, right? So if I just go mechanics, So when we talk about mechanics, we need to talk about mechanics too. We gotta talk about pressure. So pressure, the actual definition for pressure would be P is equal to F over A, where P is equal to pressure, F is equal to force, and A is equal to area. But then we have a sort of pressure in liquids. So if I have this is normal pressure. This is pressure in a liquid, right? So pressure in a liquid would be something called pressure is equal to rho GH. Yeah. So pressure, pressure rho would be density. It looks like a P, density of liquid. We know that G is acceleration due to gravity. Yeah. I'm just trying to do as much active acceleration due to gravity. And then H is like the depth below the surface of the liquid. Depth below surface. Yes, surface of a liquid. Yeah. Alright. So atmospheric pressure. So average value for example, atmosphere sea level is like 1 by 10 to the 5. So if you want to measure atmospheric pressure, yani we use an apparatus called a barometer. Yeah. So now we have demonstration for pressure. Yeah, for atmospheric pressure. So we have a demo, crumpling can, collapsing can. Yeah. So this demo that we're about to do is for what we call sorry, let me just grab a ruler. Demo is for atmospheric pressure. Okay. So first of all, remember, we're going to have a can, right? Can is perfectly normal, right? So you have a can. We add a few drops. We add a small amount of water, and we have kind of like a heat. So you have a Bunsen burner at the bottom. Then in the second one, what happens is, I think it's the same can, but the can fills with steam. And the first one is steam. Then we put a cap, and then it's kind of like something like this. Yeah. See, these diagrams are the things you kind of forget. Kind of crumpled up, like you kind of go whatever way you want, like really. Right. So in this one, you have steam coming out. In this one, we just have kind of like water. Yeah. So we're going to space a small amount of water into a metal can, and we're going to use a Bunsen burner to bring it to a boil, and boil this water with a Bunsen burner. Exactly. So steam is going to be driven out of. So as the can fills with steam, air is driven out of the can. Fine. We're then going to turn off the Bunsen burner, and we're going to place a kind of a stopper and put a tightly. So this is a tightly fitting lid on the can. So all of the steam condenses back down into water, leaving behind a partial vacuum in the can, and the can becomes crushed as the atmospheric pressure as the atmospheric pressure outside the can is greater than the pressure inside of the can. So yeah, I mean what we're saying is essentially I'm going to place a small amount of water into a metal can, and I'm going to bring this water to a boil using the Bunsen burner. Now, as the can fills with steam, the air is driven out of the can. Then I turn off the Bunsen burner and I place a tightly fitting lid on the can. What happens is the water then the steam then condenses back into water, leaving behind a partial vacuum in the can, and the can becomes crushed as the atmospheric pressure outside the can is greater than the pressure inside of the can. Yeah. So let's just do that one last time without looking. So first image is you have a can, and we place like a small amount of water into it. As you can see here, we have a Bunsen burner here, okay, and it's filling with steam, meaning that's driving out the air. Then we have a second can. It's still intact, it's still in shape. It still has this water down here. Look at that. And then we have yani the last one, which is like so essentially place small amount of water in a can, in a metal can, and is it a can or a metal can? Yeah, it's a metal can. Place a small amount of water in a metal can and bring to boil using Bunsen burner. Can fills with steam, which drives out air from can. Turn off Bunsen burner and place tightly fitting lid on can. Steam condenses back into water, leaving behind basically what we're saying is we add a small amount of water to a can, we bring it to a boil using the Bunsen burner, can fills with steam, drives the air out of the can, turn off the Bunsen burner, place the tightly fitting lid, the steam condenses back into water, leaving behind a partial vacuum, and the can becomes crushed because the atmospheric pressure outside the can is greater than the pressure inside of the can. Alright, like, nice. Beautiful. We have Archimedes' principle. We'll experience an upthrust that's equal in magnitude to the weight of the water displaced. Okay. So now let's just do a sample question really quickly. We kind of need to just speed run this chapter, yeah. So for this one, so they're giving us P equals F over A. So they give me 50 kg person. So P is equal to F. So F is equal to MA. So it's in 50 in kilograms for us. Amazing. 9.8. P equals F over A. So that means pi 0.02 squared. P is equal to, I'm kind of just in a rush, bro. I can't lie. 9.8 all over. I hope that if I do these questions, I should be able to answer what's in the leaving cert, but something that I did these chapters a while back, so I just want to refresh them. I did them like a month ago, so I mean I still know all the stuff basically, like I mean, but especially like just the maths questions and like pascals, I guess, and then that's part 1, and then part 2 stated that it's a 5-ton guy, the elephant, sorry, 9.8, and it's a pi of 0.2 squared. Yeah, okay, it's the same. Alright, then it says assume you had the density. Assume you had the density of the gas around the Earth constant value of 1.2, yeah? And calculate the height of the Earth's atmosphere. The pressure is this, so height. So P is equal to rho GH. So P is equal to rho G over H. So pressure is 1 by 10 to the 5, which is like the temperature is the pressure at sea level, I'm pretty sure. Then rho is the density, so 1.2 multiplied by the gravity, which acceleration due to gravity, which is that. It's not gravity, it's acceleration due to gravity. Oh man. 1.2 by 9.8 is equal to 0.4 meters. Yeah, above 3. Yeah. Then we have this column of mercury. Calculate the pressure due to a column of mercury. So rho, so density give me 1.36 by 10 to the 4. Rho G 0.76. Make sure your units are correct, bro. That's the one thing that always bogs people down, man. Their units are incorrect. I'm saying that other people, bro. It's gonna be me, bro. Man, 101292.8 pascals, yeah. And then we have this. Don't need to know this, screw that. If I don't need to know it, I don't need to know. So systolic pressure is the pressure that the muscles of the heart chambers exert when the heart is systolic, meaning contracting, and the pressure that the muscles of the chambers of the heart exert when the heart is relaxed, when the heart is relaxed between beats. Is how much pressure your blood is exerting when the heart beats. Diastolic indicates how much pressure your blood is exerting while the heart is resting between beats. Systolic blood pressure is how much pressure your blood is exerting when your heart beats, and then diastolic pressure is how much pressure your heart is exerting when your heart rests between beats. So 122.79, yeah. Your blood pressure measures this. Convert both of these readings to Pascal. So P is equal to rho GH and P is equal to rho GH. So it's equal to rho density, which is 1.36 by 10 to the 4, 9.8. Height, so this is going to be systole, and this is going to be diastole, yeah. Systole is going to be higher always because the muscle of the heart's contracting, yeah. So it's contractile muscle. Okay. Anyways, where was I? Oh yeah, 122 by 10 to the minus 3. Actually, no. Wait. I'll leave that to last. So whichever one's higher, then we can determine, because I don't want to already do something wrong and then crying over it or something. Stress is getting to my head, bro. I just want to be at peace with myself, bro. Right now I'm not. I'll be honest. I can't even sleep, bro. I couldn't even sleep at night because of the stress, because the thoughts in my head, man. You guys may be like, oh my god, this guy, like, he's getting the work done. So Archimedes' principle states that when an object is floating in air, sorry. When an object is immersed in a fluid, it will experience an upthrust that's equal in magnitude to the weight of the fluid displaced. And law of flotation states that when an object is floating on a liquid, it's the weight of the object in air is equal to the weight of the fluid displaced. Wow, I actually remember that. That's crazy. Nice. We have Boyle's law, which is for fixed mass of gas at a fixed temperature, pressure is inversely proportional to 1 over V, which is fine. So let's say I have when an object is immersed in a fluid, it will experience an upthrust that it'll experience an upthrust is equal in magnitude to weight of fluid. Now fluid can be liquid or gas, yeah? So that's why don't say water, fluid displaced. Okay. So you're using some sort of a Newton spring balance. So let's say I see my object here. Bang, 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 bang. Is this mechanics 2, yeah? Yeah, it's mechanics 2. So it says that, okay, object is 8 newtons in here. Right? So let's just draw. Still look at the draw, cause yeah. So now it's immersed in the fluid. Yeah, you see that. So now it's like bang, 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 bang. I don't know, bro. I'm stressing, man. I'm stressing. So the upthrust. Yeah. So now the object is 6 newtons in water, but the upthrust is 2 newtons, but then 2 newtons of water displaced. So the object is 8 newtons in water. I then immerse it in the fluid. I immerse it in the water. Now the object is 6 newtons in water, but the upthrust is 2 newtons, and the weight of the water displaced is also 2 newtons. So we know that the object weighs 8 newtons in the air. When the object is immersed in the water, the weight of the object is now 6 newtons. This means that the object is experiencing an upwards force or an upthrust of 2 newtons. The water is exerting an upward force of 2 newtons on the object. This force of 2 newtons is called the upthrust. The weight of water displaced also 2 newtons. This shows that the upthrust equals weight of the water displaced. So essentially, Upthrust is equal to weight of none. I don't give up, man. You know. Well, that's my lingo. Cause you don't give up. That's not in my blood. Even when the odds are against you. Like I probably have nothing to worry about, right? But I'm just like stressed out. Oh, whatever, bro. Something like that. Just kind of like do like you catch the lingo, cause you catch the lingo. Um, on water. Technically not in the water, but yeah. So what was it? Weight of object in air. Well, it's crazy how your memory works. How I still know it. I just needed to like jog the memory. Weight of object air is equal to weight of water displaced. Oh man. So we said that we used a barometer to measure atmospheric pressure, but now what are we going to use to measure the density of a liquid? We're already on page 6, which is crazy. Density of a liquid is equal to a hydrometer. Aki. Ak. This is emergency zone, you get me? So let's say, okay, so block of concrete, the water above above the block puts a pressure on the top of the block. The water cause so the upthrust is equal to the downwards force, the upwards force on the bottom minus the downwards force on the top. So upthrust, yeah, is equal to the oh my god, so stupid. Yeah, oh yeah. Upthrust is equal to upwards minus up thrust is equal to upwards force on the bottom minus downwards force on the top. So now we have, so if the up thrust is greater than the weight, the object floats. If the up thrust is less than the weight, the object sinks. Yeah, exactly, yeah. So sample question 5. Oh. Okay. Let's go. A cube of size 1 meter is fully immersed. Yeah. Cool. On the top of the cube by the, so we know it's in a liquid. So rho GH. Probably give us some. Yeah. Okay. So P is equal to 1,000. 9.8, and H is going to be 3 meters because it's at the top. Yeah. Yeah. And then 2 is the downward force on the top, so the upward force on the bottom. Okay, because the sides are 1 meter, it's just 4 meters now. I don't know why I'm streaming or why I'm doing any of this, but like, it's just fun, bro. It's just good crack, man. You get me? So Boyle's law states for a fixed mass of gas at a fixed temperature, pressure is inversely proportional to volume. We know that, man. Another equation you can use is that P1V1 is equal to P2V2. That's the one that we use for most of the equations as well, yeah? And come on. Alright, let's do it. It's not in the last tables as well. It's kind of bullshit. Alright, so it says, for this one, I think you can just use centimeters cube. So it says 4 centimeter cube. Okay. Sorry, that was a bit weird. Alright, 1.2 by 10 to the 5. And I divide that by 2 by 10 to the 5. You guys never procrastinate. This is what happens. I mean, I probably would be revising near the exams, but it wouldn't be this intense. Like, that's just stupid. Oh man, this is some cheeky 2006 question. Yeah, I've done this like 10 times before. If I don't realize that like the size is getting 3 times smaller or whatever, a small bubble of gas rises from the bottom of the lake. The volume of the bubble of gas increases threefold when it reaches the surface of the lake. Now, with the atmospheric pressure is 1.01 by 10 to the 5. So if so at top the volume x3, but the pressure divide by 3. So at bottom volume يعني divide by 3, pressure multiply by 3. Yes, come on, man. Okay, alright. So it's just 3.03 by 10 to the 5 pascals. Now it says the depth of the lake. Now this is a trick question because pressure is equal to, oh no. P over rho G is equal to H. Pressure is actually 4.04 because you have to count the surface as well. P is rho is 1000, 1 by 10 to the 3, and then G is 9.8. Now you have Boyle's laws. No. No, it's no. I did the opposite. I did the opposite way. It's okay. It's okay. It's okay. It's okay. It's okay. So we just minus that pressure at the top. Yeah, that makes sense. That makes sense. So it's actually 2.02 by 10 to the 5. 2.02 by 10 to the 5. 20.61. Yeah, it's likely to come up as well, yeah? It's cheeky bastard. I know, yeah, I know. I know how to draw the diagram. And the gas is just in here. I don't know what the hell is that, bro. What the hell, bro? Like, that is not it. That is not it. So by adjusting the gas side piston, you change both the volume and the pressure of the gas, yeah? The volume of the gas is read using the graduated cell along the cylindrical container. It is acceptable to record the values in centimeters cubed. The pressure of the gas is read from the pressure gauge. The pressure is in pascals. Measure and record several corresponding values for the volume of the gas and the pressure of the gas. Plot a graph with pressure on the y-axis and 1 over volume, the reciprocal of volume on the x-axis, and a straight line graph through the origin verifies that pressure is proportional to 1 over volume. Accuracy is to use a gas-timed piston to keep the mass of the gas constant. Use a gas-tight piston keeps the mass of gas constant. When the piston is adjusted, allow a few minutes for the gas to settle and return back to room temperature for a few minutes. When the piston is adjusted for another set of readings, we're going to allow the gas to settle for a few minutes. This allows the gas to return to room temperature. This keeps the temperature of the gas constant. Avoid the error of parallax when reading the pressure gauge and when reading the volume of the gas from the calibrated scale along the cylinder. Avoid very small values for the volume as they result in greater percentage errors when using calculations. So essentially, when we adjust the position of the gas tight piston, we're adjusting both the pressure and the volume of the gas. Now, the volume of the gas is determined by reading the graduated scale along the side of the cylindrical container. This is measured in centimeters cubed. It's acceptable. Pressure is got from the pressure gauge, measured in pascals. Now, what I'm going to do is I'm going to get several corresponding values for pressure and the volume, and then I'm going to plot a graph with pressure on the y-axis, 1 over volume on the x-axis, 1 over volume, and the straight line graph with the origin verifies the pressure is inversely proportional to 1 over volume, to volume. The volume is inversely proportional to pressure, whatever you want to say. Right. Precautions is when the gas tight piston is adjusted for another set of readings, we're going to allow a few minutes. We're going to allow the gas to settle for a few minutes. This is to allow time for the gas to return back to room temperature. This keeps the temperature of the gas constant. Using a gas-tight piston ensures that the mass of the gas remains constant. We're going to avoid the error of parallax when measuring the pressure of the gas using the pressure gauge or reading the volume of the gas along the graduated scale along the cylindrical container, and avoid using very small values for volume, as smaller values lead to greater percentage errors in calculations. So remember, when we adjust the gas tight piston for another set of measurements, we're going to allow a few minutes for the gas to settle. This is to ensure time to allow it to return back to room temperature to keep the temperature of the gas constant. Okay. Is there anything I need to know? No. It's simple like class experiments. Not really anything to write home about. I don't think so, but oh, is that it? Bet. So we have then T equals FD, M equals FD. So a moment of a force is a perpendicular distance between the line of action and the moment force in the also this is like torque. So moment M is equal to moment of a force, F is equal to force, and D is equal to perpendicular distance from line of action of force to the axis. So M is equal to moment of force, which is measured in Newton meters usually. M is equal, if you don't even know, like F by D, N by M, Newton meter. Yeah, exactly. So is equal to F is equal to force, and D is equal to perpendicular distance between line of action of force and axis. Then we have a moment of a couple as well. T equals FD. So they're parallel but equal in magnitude. They never meet. They parallel but acting in opposite directions. They do not meet head on and they're equal in magnitude. So T is equal to well, I'm battling right this second. Yeah, it's so difficult to focus, but I'm giving it my everything. Okay, features is equal in magnitude, never meet head on. They're equal in magnitude, never meet head on. Another feature would be that, but in opposite directions. Oh, they're parallel. So think about a moment of a couple is that the line, right? So those two forces, right? They are equal in magnitude. They never meet head on. They're parallel, but they're traveling in opposite directions. And the perpendicular, and then the distance in the t equals ft is the distance, perpendicular distance between the lines of actions. All right, so that's fine. Good. So a lever is like a device that's used to amplify the force, right? A lever is a simple machine consisting of a rigid body and a fulcrum or axis, which is free to rotate about a fulcrum or an axis. Lever may be used to amplify a force. So a lever is a machine that consists of a rigid body, which is free to move about a fulcrum or axis or a point, and is used to amplify force. So laws of equilibrium states that the vector sum of forces in any the vector sum of the forces on any point on the object is equal to 0, and the sum of the moments of the forces about any point on the body is 0. The vector sum of forces in any direction on the body is 0, and the sum of the moments of the forces about any point on the meter stick is equal to 0. Oh, not meter stick body, but we use a meter stick. The vector sum of forces in any direction on the body is 0, and the sum of the moments of the forces in any direction on the body is equal to 0. No, about any point. But yeah, that makes sense. First of all, vector sum of forces in any direction on one. So laws of equilibrium states that the vector sum of forces in any direction of the body is 0, and the sum of the moments of the forces about any point on the body is equal to 0. Okay, nice, done. So that means that if, let's say, the body is in equilibrium, it'll be in no motion or in a state of constant motion, or have no rotation and will be in state of a constant rotation. So no, uniform rotation, or no rotation or uniform rotation. Um, no motion or uniform motion. Okay, so but you usually look at no motion, no rotation, but technically speaking, okay. Uniform meter stick means that the center of gravity is on the 50 centimeter mark. I'm already about to fall asleep, bro. Can't lie, cuz fulcrum is here. So this is anti-clockwise, this is clockwise, this is clockwise, and this is anti-clockwise. Yeah. So I'm gonna say upwards forces equal to I need to do 5 chapters today, which is crazy work. Don't get me wrong. It's not easy. Don't get me wrong, but it's doable. 32 is equal to and then Bro, stress harass it's oh my god, bro. It's bad. But I'm pushing through, I'm pushing through. Come on. Never give up, man. Never give up, man. Hope is on the horizon always, cause I don't know if I need to include the center of gravity. I don't remember that, so I mean we'll find out anyways. It'll work out perfectly fine, but so the vector sum of forces in any direction of the body is equal to zero, and the sum of the moments of the forces about any point on the body is equal to zero as well. So now we have experiment to demonstrate to investigate the laws of equilibrium. So we're gonna have from my memory. This is from my memory. I'm not gonna look at the diagram, but I remember it has some sort of retort stance here, and you need these for full marks. But the diagram you're not gonna show the center of gravity, yeah. And I'm just gonna put this down for like funsies, but if they said draw the diagram, I would not put this in. You don't put this in. If they say that, then you just get rid of that because of course you can't see that. You can't see the center of gravity, which is which is crazy, yeah. So these are the weights. Well, I keep on having dreams about I don't know, man. What's going on? Man, I was like something random. What was that? Yeah, so we're going to move the weights and the Newton balances along the meter stick until the meter stick is in horizontal equilibrium. Note the values of the weights hanging from the meter stick and the positions they hang from. Note the Note the readings on the Newton balances in the position along the meter stick. Note the weight of the meter stick and its center of gravity position. The downwards forces is the sum of the hanging weights, and the upwards force is the sum of the values on the Newton spring on the Newton balances. The upwards forces equals the downward forces. Choose a fulcrum or axis. Calculate the sum of the clockwise moments and the sum of the anti-clockwise moments. The clockwise moments equals the anti-clockwise moments. The values of the weights should be changed. The values of the weights and the position should be changed and the calculations redone. Repeated. Always have the meter stick in horizontal equilibrium. Hang the weights with a thin non-elastic string to determine the position along the meter stick more accurately. And then locate the point of suspension very accurately and avoid using weights of very small values. The small values lead to greater percentage errors. First of all, we're going to change the weights and their positions and redo the calculations. We're going to then and then time, procedure, and calculation repeated. Always have the meter stick in horizontal equilibrium. Hang the weights using a non-elastic or a thin non-elastic thread, and this will allow you to locate the point of the suspension more accurately and avoid using small values for the weights as smaller values lead to greater percentage. So adjust the values of the weights along the meter stick until the meter stick is in horizontal equilibrium. Note and record the values of the weights and their position along the meter stick. Note and record the values on the Newton balances and their position along the meter stick. Note and record the weight of the meter stick in the center of gravity position. The sum of the downwards forces, just the sum of the weights, is sum of the weights, and the sum of the upward forces, the sum of the values on the Newton balances. Upward forces should be equal to upward forces equal to downward forces. Calculate the clockwise. Choose an axis or a fulcrum, and calculate the clockwise moments and the anti-clockwise moments. And the clockwise moments should be equal to the anti-clockwise moments. Now, for the accuracy is you change the value of the weights and the position, uh, and the procedure and the calculation should be redone. We're going to ensure that the meter stick is in horizontal equilibrium. We're going to use a non-elastic or thin thread to accurately determine the point of suspension of the weights along the meter stick and avoid using very small values for the weight as smaller values lead to greater percentage errors. Bro, I don't know what is going on, cuz. No, anti-clockwise. What do you have circular motion? Alright, come on, lock in. I'll do a bit of meditation after this, cause once we've done this chapter, calculate the sum of the upward forces and the sum of the downward forces. I mean, 6 newtons is equal to 6 newtons, I guess, and the vector sum of the forces at any point on the body is equal the vector sum. I don't care because I'm not going to really be using these notes again, so clockwise, anti-clockwise, anti-clockwise. One chapter is taking. When my efficiency goes down, cause it's hell, man. It's hell. But the rest of the chapters I find easy. Proper apnea, bro. Because you allow for experimental error, that's why they're Calculate the sound of clockwise movements and sound to the 10 centimeter mark on the meter stick. Oh, I'm not bothered to do that. I didn't read that. Of course, in an exam I'd read the question, but no, not really. So, we're already here. Yeah, this arc length over. So, page 51. Angular velocity is equal to estimated in radians over a second. So change angular displacement, t is equal to time. So then the unit of measurement is rads minus 1, because change in angular displacement is measured in radian, time in second if you divide the two, s minus 1. Yeah, so derivation, so angular velocity is equal to the change in angular displacement over time. Angular velocity is equal to angle can be written to S so we actually replace the theta with S over R, S over RT, V over T, no, V over R, yeah, okay. So the periodic time so it says a particle is traveling in a circular motion on So it says the angular velocity. A disk of diameter 30 centimeters rotates at 32 revolutions per minute. Correct, yeah, apparently the linear speed. Yeah. It takes 24 hours, right? Mm-hmm. If the radius of the Earth calculated. Why is it so hard, bro, to do this? Centripetal acceleration is the acceleration that's acting towards the center of a circle for a body undergoing circular motion. Uniform. Centripetal acceleration is the acceleration acting towards the center of a circle for an object undergoing uniform circular motion. Centripetal force is the force acting towards the center of a circle for an object undergoing circular motion. Oh, man, I know. I am trying to push through. We're going strong though. We're going strong. We're going yart. Oh, tame yart, bro. From strength to strength. Yesterday I studied on trio and I studied what was that fella's name? Yeah, Harlamabok as well, yeah. So I just have Oshina Dir Nanog left and one essay paragraph left, and I'm basically done everything for Irish. Then I just need to do some listenings and some comprehensions and question 6Bs. Other than that, you know, you never get enough of those. A car of mass this, so M is equal to 1600, V is equal to 24, R is equal to 15. Calculate centripetal force needed. So yeah, mv squared over r. F is equal to mv squared over r. F is equal to 1600 multiplied by 24 squared all over 15. F is equal to 1600 multiplied by 24 squared all over 15. 61440 newtons, and then right. Then it says a stone mass is attached to the end of a string and undergoes circular motion. The radius of this, calculate the tension in the string. So I need the force, right? So I got mass is equal to 5, undergoes circular motion. The radius is equal to 1.6. And, oh my god, that's equal to 6. So gravity is acting down and centripetal is acting down. See T plus mg. Here, centripetal is acting up, but gravity is acting down, so T minus mg. So at the top, tension is 5 mr So this is max T and this is min T. That's crazy how we're already on planetary motion, bro. And then we just have simple harmonic motion to go. I'll be back. I'm back. Alright, let's go. Okay. So it says a diagram is below shows, okay. So 0.24 is the mass, so sample question 8. So the mass is equal to 0.24. This length of the string is equal to 0.8 meters. And V is equal to 5 meters squared. So the length of the string is that much. Now, what is the velocity of the body? So the velocity is going from here to here, but really it's continuing on as well. So how do we approach this? So first of all, we're gonna have we have a kinetic energy. Kinetic energy is going to give us mgh plus more kinetic energy. Yeah. So then what you can do is you can cross out the mass in all of these, from what I remember, and you can multiply everything by 2. So you get v squared is equal to 2gh plus v squared. This is all I remember. Now v squared, actually, you know what? I won't do that because then it will get confusing. Half mv squared is equal to mgh plus a half v squared. So a half by mass, which was here 0.24. And my initial velocity, what was my initial velocity? My initial velocity, guys, was 5 meters squared. Yeah, linear squared. Don't forget the squared. Now we have 0.24, 9.8, sorry, 9.8. But my height has become 0.8 plus a half. Of course, mass is not going to change, but this v squared we don't know. Yeah. So now I have 0. Now I multiply everything by 2. So then I have 0.24 by 25 is equal to 2 by 0.24 by 9.8 by 0.8 plus 0.24 v squared. So I have basically 0.24 multiplied by 25. So I have 6 minus 2 by 0.24 by 9.8 by 0.8, which is 3.7632 is equal to 0.24 v squared. 6 minus 3.7632 divided by 0.24, so 9.32 is equal to v squared. If I square both sides, square root both sides, square root of the answer is 3.0527, oh sorry, 9 ms minus 1. Yeah, this is centripetal acceleration. Okay. Yeah, because the diagram's the biggest bullshit I've ever seen. That's why they mistook the. That's why they mistook the diagram, cause it's the worst diagram I've ever seen in my life. I. Bet. We're doing well. 1 hour and 1.5 hour in nearly. Come on. Okay. So then we have Newton's law of gravitation. So we have Newton's law of universal gravitation. I actually like this part of the course because there's some cool like algebraic tricks that you can do. So it's actually F is equal to G m1 m2 all over d squared. So F is equal to the force, of course. G is equal to the gravitational constant, 6.7 by 10 to the minus 11, I think it is. Gravitational constant. M1, M2 are the mass values. And D is equal to distance between point masses. I haven't forgot. That's why I'm getting through the chapter so quickly, because I remember most of the shit. So G is equal to Gm over R squared, or G is equal to Gm or plus H squared. So now we have a few sample questions to get through. Sample question 1. I need to make sure my posture is good as well so we can go for a long Alright, okay. So on the surface of the earth, G is equal to 6.7 by 10 to the minus 11. Gmm, which is 6 by 10 to the 24, all over Gm over R squared, which is equal to 6.4 by 10 to the 6 squared. 6.7 by 10 to the... Imagine not squaring it, bro. That's gonna be hell, man. I always forget to square stuff. I was putting a minus there by accident as well. Which is equal to 9.81. Don't forget it's minus 2, yeah? No, it's 200. Huh? Now for this one, don't forget, I'll show you a thing, yeah. Meters squared. Everything's the same, plus sample question 2. Calculate the gravitational attraction between the Earth and the Moon and the Moon and the... I sound like I'm dying, bro, but like... Math it... We're gonna have to do some past papers as well, hopefully. And the distance between the Earth and the Moon is 375. Ding, ding, ding. Multiply by 10 to the 3 to get that converted into meters, and then to square that as well. Why did I clear my... No, I probably would have messed up something. It's always better to do it from scratch. Foreign, you might save a bit of time, but the probability that you leave something in there that's not meant to be there is too high. Look, I know I say nothing risked, nothing gained, but to be honest with you, when it comes to school, bro, I don't want to be risking shit. So when it comes to my career, I don't want to be. No, I risk shit. That's why I'm doing this right now. I could have done this earlier. I could have already studied the whole course, but me being a lazy bum that I am, I just kind of left it to the last minute, and yeah, that's why we're here right now. Yeah, so the weight of an object in space is 9 times smaller. So on top, we're gonna have gm over r squared. It's a difficult question. Nine g over g. So if I flip it, then there's no g. Then we got 9r. Yeah. Now find the square root of both sides. I get uh, r plus h over r is equal to 3. So then r plus h is equal to 3r. And then I need h, so I get h is equal to 2r. Yeah, I did it right. I am shocked. I'm shocked, to be honest with you, because I never get that right in the first try. But I guess I've done it so many times now that I kind of just get the gist of it. As you get a paw. Gonna get a gonna travel like a Gina. I don't know what to say when I'm feeling. Everything is looking like oh, 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 I was stuck up in I don't know, I don't know, I don't know. Everybody's it's gonna be like 9.22, I'm pretty sure. Yeah, I'm making the same mistakes I say not to make. So why does the ISS appear weightless? It's like basically the ISS is located 200 kilometers above the surface, 400 kilometers above the Earth. So the ISS releases a rocket which projects it along a tangent line. Then it travels along the tangent line and it drops down towards at the same time. The Earth down at the same time. It then travels along another tangent line and then drops down to the Earth at the same time. However, the distance that it falls down to the Earth is small enough to ensure it never actually gets closer to the Earth. So therefore, the ISS travels in a circular orbit around the Earth. It's something like that. The Oculus fires the ISS projectile on a tangent line as listed above. The ISS moves along this line, falls to the Earth at the same time. The momentum of the ISS moves along another tangent line. The ISS moves along this line and falls to the Earth at the same time. This combined motion continues on and on. The distance it falls to the Earth each time is just enough to ensure it never gets close to the Earth. I've never drawn the diagram though. I'll be honest with you. Yeah. So the ISS fires a rocket which projects it along a tangent line. The ISS then travels along this tangent line and falls down towards the Earth at the same time. The momentum of the ISS causes it to travel along another tangent line. It travels along this tangent line and then falls to the Earth at the same time. However, the distance that the ISS falls down towards the Earth is small enough to ensure it never gets actually closer to the Earth, and this motion continues on, and therefore the ISS moves in a circular orbit around the Earth. And the ISS is located 400 kilometers above the surface. Sample question 5. I don't know why I feel so stressed, bro. I don't know why. I don't know why. Genuinely, bro. I'm so lost. Should I do the past papers at the... No. You calculate the acceleration due to gravity, which is at a height above the surface of the Earth, which is 5 times gm over 5 times, so 6r squared all over gm over r squared, gm over 36r squared all over gm squared, 1 over 36r squared over 1 over r squared. I can hear him. We're nearly done the chapter, which is honestly amazing. So satellites. So we study the motion of satellites. So the moon is a satellite to the Earth is a satellite to the sun, and the ice is a satellite to the Earth as well, right? So we have the derivation. So we have a derivation. Derivation, which is periodic time is proportional to radius of orbit cubed, right? So first of all, we're going to say force gravitational force between, let's say I say gravitational force between planet opposed to centripetal force keeping really should be R. I know, man. I know. I think I might just do mechanics today, then do electricity on Thursday. Every joy and trouble. The ISS orbits the Earth Wow, stress is getting too much, bro. I need to go for a walk, bro. I can't lie. I'm just not feeling too good right now. Anxiety, just why is anxiety? I'm literally studying, bro. I'm literally studying. I'm literally getting my work done, getting my shit done. And yet still with anxiety, it's like you can't do this. You can do this. You'll never be able to do this. Yeah, that's my life, man. Every day, my head just tells me that I can't do it, man. Like, it just gets too much sometimes, you know. Yeah. So geostationary satellite is a satellite that appears to be stationary above a certain point on the Earth. They give the illusion of being stationary above a certain point on the. So they must have the same rotational orbit as the Earth. They must orbit the Earth in the equatorial plane, and they must move in the same direction as the Earth's rotation. So, same rotational period as the Earth, 24 hours. They must move in the same direction as the rotation of the Earth, and they must orbit the Earth in the equatorial plane. Okay. Oh, frick. There's a satellite in it, so. See, I can't even think straight, bro. So geostationary. Bro, I'm struggling, man. We're getting through it though. I know, like we've probably been studying for like 2 hours now, probably. Nearly, yeah. Not even. But I was a bit behind. Go from. Oh, we're nearly done. One chapter took 2 hours, bro. And then a lot of mechanics 1 past paper, so I won't worry with that. But mechanics 2 I haven't done, so one of the moons of Saturn is in an orbit which approximately the same radius as the Earth's moon. Seriously, cuz why? Okay, so one of the moons of Saturn is in orbit that has approximately the same radius as the Earth's moon. Given that the speed of Saturn moon is 10 times, okay, so 10 VE over VE is equal to square root of GM over R. So both are square roots, so they cancel out. So GM but this is Saturn and this is Earth. This is right. I'm actually gonna be proud of myself. And if it's wrong, I'm gonna be sad to myself. No, I squared everything, so then I have to square this as well. To multiply by 100 as well. So 100 by 100. 6 by 26, yeah. Every joy and trial, the stars are shining and hidden place the way. There's only one thing I can. I don't know, man. The anxiety is getting worse and worse, bro. I know, man. I'm struggling. I genuinely am, bro. But I'm pushing through. I don't give a shit, man. Alright, so what are some examples of simple harmonic motion? Would be a weight vibrating at the end of a string. We could have a pendulum bomb swinging to a small angle. We could have a tuning fork vibrating, or we could have a vibrating stretch string. So a weight hanging at the end of a spring. We could have a vibration of a stretch string. We could have a vibrating tuning fork, and we could have a pendulum bob swinging to a small angle. So simple harmonic motion states that is the motion of an object where the acceleration simple harmonic motion is a motion of an object for which its acceleration is proportional to its displacement from a fixed point, and that the direction of the acceleration is opposite to the direction of the displacement. So simple harmonic motion is the motion of an object for which its acceleration is proportional to its displacement from a fixed point, and the direction of the acceleration is opposite to the direction of displacement. Now, why does direction matter? Because both of these are scalar quantities. Both of these are vector quantities. They both have magnitude and direction. So, if we come here, the equation is equal to constant of so A is acceleration, S is displacement, and constant proportionality. Minus just says that they're going in the opposite directions. So periodic time, T is equal to 1 over F. But remember, we looked at this per unit time. Angular velocity is equal to 2 pi over T. T is equal to 2 pi over, yeah. So those are two equations, yeah. So particle undergoes simple harmonic motion. We just have one more experiment left. And then we'll do like some, I think I'll do like 1 hour of past papers maybe. We'll do 1 hour, we'll sweat out 1 hour of past papers, and I think I'll be done with mechanics class. Well, mechanics 2. So sample question 1 says a particle undergoes simple harmonic motion when it is 5.4 centimeters. So A is equal to, you don't need the minus, right? So so the distance is 0.054, and the acceler, oh no, because it's in centimeters per second. So acceleration is equal to 2.8. So period is t is equal to 2 pi over, now what's the angular velocity? Now angular velocity is, I'm just playing around with numbers right now, you know, like I don't know if I'm right or I'm wrong. We just have to play around. No, it's actually not, because it's actually 0.518518. That's what it means. So it's like 0.518518, which is equal to 12.118 seconds. Well, that's completely wrong. What the frick? Oh, that's displacement. I thought that was speed. See, this shows how the stress just gets to you, bro. Bro, I'm better than this, man. So I need to get the constant of proportionality, which also happens to be the same symbol as the angular velocity. Hooke's law states that if an object is stretched or compressed, its the restoring force will be proportional to the displacement if you stay within the elastic limits of the object. So simple harmonic motion is the motion that an object undergoes where its displacement is proportional to acceleration, but the direction of the acceleration is opposite to the direction of the acceleration. Now, Hooke's law states that if an object is stretched or compressed, right, its restoring force will be proportional to its displacement if you stay within the elastic limits of the object. Its restoring force is directly proportional. This one was just proportional. This was not directly. It's directly proportional to it. So I think it's like F equals minus Ks. So Hooke's law constant, spring constant, F is force, S is displacement. So by the way, The stars are shining. I was so close to finishing the chapter and being so lazy, man. Let's go for. When the restoring force on a spring, restoring force is so F is equal to 20 and S is equal to 0.06. So 20 divided by 0.06 equals that was part I, and then part 2 was the displacement when the force is 14. So 14 string obeys Hooke's law. A stress string obeys Hooke's law. Hooke's law states that if an object is stretched or compressed, its restoring force will be proportional to displacement if you stay within the elastic limits of the object. So the stress string obeys Hooke's law when a small sphere of mass, okay, so 0.3, 9.8 is equal to K S. So divide by 200 by 10 to the minus 3. 0.3 multiplied by 9.8, 200 by 10 to the minus 3. So 14.7, and m minus 1 is the spring constant. Now the sphere is pulled down until the length of it is now the sphere is released and it oscillates about first. Calculate the period of oscillation of the sphere. So t is equal to 2 pi over 2 pi over omega, I think it is. So the period of oscillation. So I basically know that this is equal to k over m. So this is equal to the spring constant all over the mass, which was 0.3. So 14.7 divided by 0.3, and find, so yeah, so which is equal to 2 pi over 7, which is equal to 2 pi over 7, which is equal to 0.898 seconds, I think so. What the frick? Yeah, but I got, oh, that's part A. So I didn't even get the right spring constant. Oh, shit. I didn't read that. Man, frick's sake, man. It's okay, it's okay, it's okay. It's okay. Happens. Shit happens, man. 9.8, and then we divide that by 85 by 10 to the minus 3. That should give me a spring constant of, yeah, 34.589. Now 34.589 square root of 34.589 all over 0.3. So 2 pi over 10.737. 2 pi over 10.737 is equal to 0.585 seconds. Is that correct? Yeah, it's correct. Now it says B. The maximum acceleration of the sphere. So centripetal acceleration. No, it's not centripetal. Oh, why did you? No, I don't. No, I don't. But why? Thank God. The length of the spring when the acceleration of the sphere is 0. 285 millimeters. Has to be. Yeah. 0 displacement. So 0 displacement. We have one last experiment. One last time. Oh man. So experiment 2. Split cord, pointed suspension, taut string, and pendulum bob. So we have a retort stand, we have a split cork, we have a pointed suspension, we have a taut string, and we have a pendulum bob. And then all of this apparatus, and then of course don't forget your timer as well. Just something like this simple. Because it is periodic time is proportional to length. Oh, this could come up. This could well come up, bro. So first of all, allow the pendulum to swing from side to side through a small angle. The length of the pendulum is varied in order to gather a set of data. Measure and record the length of the pendulum from the pointed suspension to the center of the bob, to the center of gravity of the bob. Measure and record the time for 40 complete oscillations of the pendulum. Repeat this procedure for several different values of length. So allow the pendulum to swing from side to side through a small angle, and the length of the pendulum was varied to gather a set of data. Now, we're going to measure and record the length of the pendulum from the pointed suspension to the center of gravity of the bob. Measure and record the time taken for 40 complete oscillations of the pendulum. And repeat the experiment for different lengths of the pendulum. Now, graph is then set up like this, yeah? And now, what we have on the y-axis is length in what we call meters. On the x-axis, we have periodic time squared in seconds squared, periodic time squared in seconds squared. Now, a straight line graph to the origin verifies that length is proportional to periodic time squared for a pendulum, for a simple pendulum. So length is proportional to periodic time squared. Now, it is better to measure the time for several oscillations of the pendulum rather than just one. These larger measurements of time result in smaller percentage errors. Using larger values of the length of the pendulum. Using larger values of the length of the pendulum will result in smaller percentage errors. Yeah, it makes sense. Large values, small percentage errors. Avoid the error of parallax when measuring the length of the pendulum from the pointed suspension to the center of gravity of the bob. Keep the angle of the swing small, less than 5 degrees, to ensure that the pendulum is undergoing simple harmonic motion. Use a heavy bob to keep the string taut, and use a small bob, so heavy and small, to reduce the effects of air resistance on the bob, and use inextensible string or taut string to ensure the length of the string remains constant. Alright, so we're going to record the time taken for 40 complete oscillations as opposed to one. As larger values lead to smaller percentage errors. I mean, avoid using smaller values for, yeah, avoid using smaller values, so the length of the pendulum as smaller values lead to greater percentage errors. Avoid the error of parallax when measuring the length of the pendulum from the pointed suspension to the center of gravity of the bob, and ensure that the pendulum is swinging to a small angle, so less than 5 degrees, to ensure the motion of the pendulum is simple harmonic motion. Ensure that the pendulum bob itself is heavy to keep the string taut. Ensure that it is small to minimize the effects of air resistance on the bob, and also use inextensible string to keep the length of the pendulum constant. Now, they're going to ask us to calculate the acceleration due to gravity. Yeah, so we know that t is equal to 2 pi L over g. But you know it's going to be L over t squared. So if I square both sides, yeah, like basically, so t squared is equal to 4 pi squared L over g. G is equal to 4 pi squared L over t squared. Can't lie, that was hell, man. I cannot lie to you. That was absolutely hell. Like, it shouldn't have been hell, but for some reason, bro, I'm just completely out of it, man. Completely off of it, bro. I'm completely gone mental. Oh, man. Oh. It's just difficult, cuz. It's just difficult. It's difficult. Yeah, yeah. I'll just do the past papers later, bro. I can't lie. Kind of just need to keep on working, chipping away at this. I can't lie. I definitely need a break. I'm gonna go AFK for a bit. Alright guys, hey, what's going on guys? Welcome back. I just took a cold shower. We're ready to go in again. And yeah, we're ready to get this done and dusted. So let me just drink some water and I'm gonna get straight into mechanics 1. And that'll be mechanics done then. Mechanics 1 is easy. Electricity 1 is easy. Still 15 days including today, so well more than enough time if I just stay focused. So alright, so a vector quantity is a quantity with both magnitude and direction. So for example, displacement, velocity, acceleration, force, a moment of a force, magnetic flux density, and electric field strength. Yeah, that's literally it. A scalar is a quantity that is a quantity that has magnitude but not direction. For example, time, mass, temperature, work, energy, power, all these different things. So essentially, if you want to add vectors, if they're moving in the same direction, yani, you can just add them. So you always add them. But if they're moving in the opposite direction, you kind of subtract them. So that's kind of that. So it's 6 Newton west. It goes 2 newtons to the east, and then that's just 14 newtons to the east. Yeah. So we have a triangular law and we have a parallelogram law. Don't worry too much about it. So sample question 4. I mean, I want a bigger pencil, but kind of this pencil is just not it. I have a new pack of pencils, right? I actually have a brand new pen as well. Let's just use this. Alright. So sample question 4 is stating that we have to find the resultant of 4 Newton east and 4 Newton north and 4 Newtons acting northeast. So think about it this way. Just draw these as arrows. So first of all, you have to get your north, south, east, west kind of correct. So north, south, east, west. Yeah? Just draw this. This will help you a lot in the question. Now it says 4 newtons east, yani something like this, and it's 4. And then it says 4 north, like that. So 4. So you need to get basically the resultant of that. So you get basically 16 plus 16 is equal to, let's say x squared. X is equal to root of 32, which is equal to, I think it's 4 root 2, but yeah, 4 root 2. 4 root 2. Yeah, beautiful. So 4 root 2 or 5.656. Now, we know that this is north, yes, north of east, right? So when you give a vector quantity, there's both magnitude and direction, right? So essentially both of these are going in the same direction. They're both going in the same direction, so we add them. So we get 5.656 plus 4, which is equal to 9.656 north of east. .45 degrees north of east. I forgot the angle, my bad. Alright. Now sample question 5 is kind of interesting in that it says find the vertical component and horizontal component of 100 Newton force acting at an angle of 30. So the way we do this is you have something like this. Oh, this is the beautiful chapter with projectiles and all that. Alright, so this is it, right? This is kind of what we have. We have an angle of 30 degrees as we stated, and we had then this 100 this kind of component 100 Newton like that. So we need to find y and we need to find x. So very easy. We're just gonna go first of all. Let's find x. So x is adjacent over hypotenuse. So cos of 30 degrees is equal to adjacent over hypotenuse, and then sine of 30 degrees is equal to opposite over hypotenuse. Now I do 100 cosine of 30 degrees is equal to 100 cosine of 30 degrees is equal to x, and here 100 sine of 30 degrees is equal to y. But do we find the whole thing, or do they just want that? Yeah. Oh shit, my calculator is probably in radians. So 100 cosine of 30 degrees, 100 sine of 30 degrees, y is equal to 50 newtons. And 100, just make sure your calculator is in the right mode as well, yeah? Physics, we don't tend to use radians unless we're looking at that circular motion there. 100 cosine of 30 degrees, 100 cosine of 30 degrees is equal to 86.6 newtons, yeah? An object, and then we have sample question 6. So there's an object, so inclined surface, yani object here, it has a weight going down of 10. Now this object has so this is 40 degrees here, and then you see this is going to be 40 degrees in here as well. And then it says calculate the common weight acting along. So acting along would be this. So it'd be opposite over hypotenuse. So sine of 40 degrees is equal to opposite over hypotenuse. 10 sine of 40 degrees is equal to x. 10 sine of 40 degrees. So x is equal to 6.428 newtons. Yeah, that's correct. Now, it says that sample question 7. It says that pendulum bob is displaced to one side, so the string makes an angle of 10 to the vertical. So straight away, I'm thinking something like this, as a 10 degrees here. Yeah, the weight of the bob is 6 newtons. So this weight here, yani 6 newtons, and 10, and calculate the component of this weight that causes the bob to move down. So what's actually really beautiful about this is, of course, the 6 is acting down. You know, it's gonna be like something like that. 6 x 10. So it's opposite of hypotenuse. So sine of 10 degrees is equal to opposite over hypotenuse. So 6 sine of 10 degrees is equal to 6 sine of 10 degrees is equal to, yeah, that's correct, yeah, 1.04, yeah, 1.042 newtons. It's not light. I won't say it's light. Like some people will be like, oh, it's light, it's light. It's not light. Nothing's light in this life, bro. Nothing's easy. It's all subjective. Some people it's really hard, man. Some people it's really hard to study and sit down, and yet they still try and they still work hard. They may not get the best grades, but they try. You know? That's what matters, bro. It's about trying. It's about trying. It's not giving up. Yeah, this life, man, it will disappoint you in ways, man. But just gonna stay steadfast, bro. The river flows 3 stout, and the boat has a, so C for B, right? So I have, let's say, C, and I have B here. And let's say, what direction will it travel? So it said that the river flows so it's river is flowing 3 south, boat is flowing 4 meters to the east, basically. So we need to find this here. It has to be 5, right? So if the boat leaving, in what direction will it travel? And how long does it take to reach the other side? So يعني we have to find this angle in here. Now opposite over adjacent, so I'll go tan theta is equal to opposite over adjacent. Theta is equal to the tan inverse of 3 over 4. 3 over 4, which is theta is equal to 36.87 degrees south of east. South of east, that's our direction, yeah, which is beautiful. Now if we extend this all the way here, we'll actually form a triangle that looks something like this. So 36.87 will go there, sure. This will be 200, but we want to find this distance here. So we have an adjacent, we have a hypotenuse, we have cosine of 36.87 degrees is equal to adjacent over hypotenuse. Now x is equal to 200 all over cosine of 36.87 degrees. Now 200 is equal to cosine of 36.87, which is x is equal to 250 meters. Now we know time is equal to distance over speed. Now time is equal to 250 over 5 meters squared, which is equal to 50 seconds. And that's how you do it, boys. That's how you do it. Now the next question states that if the boat, let's just redraw this diagram. So the boat is leaving C, it's headed for B, and it wants to go to B, not headed for B, but actually wants to go to B. Yeah. So yeah, sure, it's traveling in 4 here. It's traveling 3 here. But do you notice something weird? Is that remember, B squared is equal to C squared. Oh shit, sorry. B squared is equal to C squared minus A squared. So is equal to 7. So x is equal to root of 7. So x is root of 7, which is beautiful. That's fine. So what's root of 7? We might just keep it as root of 7. You know what? Why not? Let's just keep it as root of 7. And it says, in what direction should it point? So here, now we have tan of theta is equal to opposite over adjacent. No. Oh shit. No, sorry. Sine of theta is equal to opposite over hypotenuse. So theta is equal to the sine inverse of 3 over 4. Shift sine of 3 over 4. And yeah. So the angle is 48.59 degrees north of east, which is good, which is a-okay, I suppose. And then if you want the time, is just 200 divided by root 7. So yeah, we just divide it like that, and then bang, 75.59 seconds. Oh, do I have my mind? Yeah, okay, nice. Beautiful. All right, now we have a bit of a demo to find the resultant of two vectors. Yeah. For the exam, I'm probably just gonna practice a bunch of graphs in those few days that we have. What the hell is like 30 pages long? What? This is a fatty chapter, bro. What the hell? I know we're gonna arrange the 3 Newton balances as shown in the diagram. And 3 pieces of non-elastic string. Arrange 3 Newton balances and 3 pieces of non-elastic string as shown in the diagram above. Ensure that the strings of balance 1 and balance 2 are at 90 degrees to each other. Then ensure all of the 3 strings are at rest. Pull balances 1, 2, 3, and make sure the point where the 3 strings meet is now at rest. Read the magnitude of the force on each balance and the direction in which the force is acting. You know the vector sum of the forces 1 and 2 will be equal in magnitude to force 3, but will be opposite in direction to force 3. Alright, let's draw it. I think I've done this billion gazit. When was it last asked? 20 deferred 22. Okay, it's likely. It's likely. You know they're gonna piss us off and they're gonna put it on it. I'm ready. Bring it on, cuz. Yeah. You know what I would do first? Is I would draw the two of them at right angle. I forgot they have to do the little ziggy zaggies as well. I will do that as well. Don't worry. Alright, wait. Bang, 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 bang. Bang, 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 bang. And then I think it's yeah. Bang, 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 bang. Bang, 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 bang. Like that, and that, and that. I just put a cheeky right angle there, just the examiners know, like, you know, I know what's up, like, you know. So, we're going to arrange. Alright, so let's label these. So, this, my friends, is the Newton balances. This, my friends, is the non-elastic string. And this, my friends, is called a horizontal board. I just say this is balance 1, balance 2, balance 3. Arrange 3 Newton balances and 3 pieces of non string. I just love pencil. I don't know. Especially pencils like this, a Faber-Castell pencil. It's so nice. It feels so premium. It feels so tactile. Like, you know, it's a pen. Man, no. I ensure that I just feel yeah. So we're going to arrange 3 Newton balances in 3 pieces of non-elastic string on a horizontal board as shown in the diagram above. Ensure that the strings of balance 1 and balance 2 are at 90 degrees to each other. Now pull balances 1, 2, 3. Ensure the point where the 3 strings meet is now at rest. Note and record the value of the magnitude of the values of the forces on the 3 balances and the direction of each force. And what we'll see is that the vector sum of the forces 1 and 2 would be equal in magnitude to force 3, but will act in the opposite direction to force 3. Kaze. Oh, I hate this chapter. Oh, it's a velocity time, distance time. Oh, the slope of the distance time graph is actually the velocity, and like, well, UVAST. No, UVAST, my boy UVAST from day 1G. Oh, I love my UVAST, bro. I love my UVAST. Like, so it says a car travels from A to B along a circular path with displacement is 20 meters. So that's part 2 done. Part 3 is going to be distance traveled, which is 2 pi r, so pi or or which is just 10 pi. Because that's not a straight line distance, you know. Displacement is the distance in a straight line. No, displacement is distance traveled in a particular direction. So distance traveled in a particular direction. Wait. Oh yeah, we have to put direction. I always forget. I've noticed it. So alright, let's switch back to the pen. Alright. Speed is equal to distance over time. Velocity is equal to displacement over time. And acceleration is equal to final velocity minus initial velocity time. But the last one is usually written as a is equal to v minus u over t. So v equals u plus at. V equals u plus at. V equals u. Oh, bro. Wait. No. Wait. Now we have three derivations. The equations of the linear motions. I think I'll probably do electricity 2 next, actually. Yeah, actually. Alright, yeah, so recall that A is equal to V minus U over T. So this is number 1. So AT is equal to V minus U. V equals U plus AT. Now, second was like average velocity can be written as S over T V plus U over 2. So 2S is equal to Vt plus Ut. S is equal to Vt over 2 plus Ut over 2. So ut plus a half plus ut plus a half is s is equal to ut plus a half ut squared. And then 3 is das mehr, man. What was the last equation? Oh, I've just been in the flow state now. What the hell? No, I already done that. So, what the hell, bro? What the hell? 1 by 10 to the minus 4 and 1 by 10 to the minus. No, I know how to convert between them. Like, I have my jugars. Like, but, like, there's no pressure. No pressure. Oh no, I'm doing all this, bro. So brakes are applied to a car. So 30, it comes to a rest. 0. Deacceleration, I don't know. Travel is 100. So brakes are. So we need a. So v squared equals u squared plus 2as. So z is equal to u squared plus 200s. So it's 200a. Sorry, 200a. So minus 200 over 900 is equal to a. A is equal to. No, I did it the wrong way around, bro. Can I think my brain only has a certain amount of capacity left, bro. I'm still gonna push through. I don't give a shit. Like, am I really gonna be able to do all those chapters, man? I don't know, but how long have we streamed? Like 3 hours, bro? Nearly 3 hours. Me good D. Wait, yeah. Insurgency is the world mercy to me. I can hear it come. I can't afford to fall asleep. You cannot afford to fall asleep, my bro. Alright, sample question force. But I hate these graphs, man. They make me fall asleep because, like, I don't know what it is. I don't know why I hate them. They're just so annoying. Speed. Oh. Yeah, so speed is distance over time. So 20 over 5, which is equal to 4 ms minus 1. And then it's part 1. And then part 2 was the velocity. The velocity, dude. Oh, bro. Bruh. I'm going crazy, bro. I can't hack it anymore. It's easy. Oh, it's easy. Oh, it's easy. Wait, yeah. The velocity is the straight line. And the speed is the curvy-wurvy. Displacement is straight line. I don't know, man. I'm just tired. Okay, so here we will analyze the motion of a car as it travels along a road. So the slope of the graph is equal to the velocity, I think so. Speed of the car, yeah. So here we know that the car is traveling at a uniform velocity because the slope remains the same, right? And the car does not start from rest. So the initial speed of the car is not zero, it travels at a uniform speed. It's a straight line graph passing to the origin, and the car passed through the starting point while moving. Yeah. So here the car did not pass through the starting point when moving. Here the car did not. The initial speed of the car was not zero. The car did not pass through the starting point. The car is traveling at a uniform speed. Here the car is not moving. It is at rest at a fixed distance away from the Now here is this graph shows the distance the speeds for two different cars. You know, both cars did not both cars and both cars are traveling with a uniform velocity. Sorry, with a uniform speed. And they're some distance away from the starting point. Now the point where they intersect is the point at which they are at the same distance away from the starting point, and one overtakes the other. So here uniform speed passes through the origin, passes through the starting point, and the initial speed is not zero. Here the initial speed is not zero, it's a uniform speed, and it did not pass through the starting point. Now here speed is zero, it's at rest at a fixed point from the starting point. Here uniform speed, they did not start at the starting point. The point at which they intersect is the distance at which from the starting point at which they meet, which one car overtakes the other. Yeah, so remember the slope of the graph is the speed of the car. Now velocity time graphs. Sorry, I'm just falling asleep. Alright, so the area underneath the graph is the displacement, but the slope is the acceleration. Yeah? Alright, so here the acceleration is uniform. The car does not start from rest. It's a straight line graph to the origin. Uniform acceleration. Velocity is increasing, so therefore it is accelerating. And the car starts from rest. So the car is accelerating because the velocity is increasing. It's a uniform acceleration because the slope remains the same. The car does not start. Car starts from rest because the velocity is there. Here the car does not start from rest. Here the car is traveling with a uniform acceleration. The car is accelerating as the velocity is increasing. Here the car is not accelerating and the car is traveling at a uniform velocity. And the car did not start from rest. Here the car did not start from rest. Here the car is deaccelerating uniformly, and we can see that it is deaccelerating because the velocity is decreasing per unit time. And then the car eventually comes to a rest. Here the car is accelerating for a certain period of time, then it travels at a uniform velocity, stops accelerating for a certain period of time, and then starts deaccelerating uniformly then until it goes to a rest. And here the acceleration is creating non-uniformly. Yeah. Oh my god, dude, oh my god. Oh, we actually did it, surprisingly. Sample question 6. Says a car initially at rest. No, my brother. Alright, let's do this velocity time graph. As the car it starts at rest, so the velocity is going to be 0, so it's going to be from the origin. Rest initially accelerates at 2 ms for 10 seconds. So every... Bro, the graph's not correct. No. That means that that's 20 ms minus 1 by the end of the 10 seconds, yeah? Oh man, I'm just tired, bro. I can't think straight, bro. I can't. So I'm probably gonna go with like 20, 18, 16, 14, 12, 10, 8, 4. Like 8, 4, bro. 8, 6, 4, 2, and 0. And then here is gonna be a 10. Let's just do 5, 10, 15, 25, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. So for the first 10 seconds, yeah, it travels up until 20. So it should be like this. And it travels uniformly as well, so you know slope is remaining constant. It starts from rest, so it passes to the origin like that. Then it travels at a uniform speed for half a minute. So from 10 to 40. So yes, bang, bang, like that. And then it then deaccelerates. Yeah, I need 5 seconds. Like to rest apparently like something like that, yeah. Just draw a rough velocity time graph for this information and calculate the distance traveled. Distance traveled is this area here. So I have a half base, which is 10, into height, which is 20, plus 30 by 20, plus a half, 5 into 20. 0 0.5, 10, 20, 20, 20, plus 30, 20, plus a half, 5, 20. So 750 meters it has traveled. Oh man, lock in, bro. Lock in, bro. Stop slacking off, man. I swear to God. I swear to God, bro. Wait, in a pole vaulting competition, an athlete sprints from rest and reaches 3 seconds into his vault for using. Okay. No, no, no. They want to challenge me? They wanna do that? Like. Oh, bro. Label the axis, bro. Bro, you're gonna lose marks, man. Like, come on, like. Cup on, bro. Oh, man, I need a cup on, bro. I'm actually high right now. Wait, let's go. Alright. Man, it can just be like, alright, let's just say it's just 9.2 is just here. Like, let's just I don't know, like velocity. Don't forget that. Don't forget that. Now you know what? I'm gonna do this properly. You know, like, come on, like, 2, 4, 6, 8, 10. So 9.2 is probably like there-ish. I actually think so, yeah. So then 1, 2, 3, 4, 5. Just 1, 2, 3, 4, 5. So it says it accelerates to 9.2 after 3 seconds. I just draw a vertical. Sorry, draw. Bro, I'm mixing up my verticals. Draw a horizontal line up until. Do something like that, and that's like this, and then 2 seconds. He maintains this velocity, so it's like. It's kind of nice. Kind of gets to build a graph. It's kind of cool. Now it says usually we have to calculate the distance traveled. So half base into height plus 2 by 9.2. I'm just tired, man. So this is the experiment to calculate the acceleration, velocity, and acceleration. So it's like. Oh, bro, this is bad, bro. I need to lock it in, man. I'm 15 days. Bro, I have no energy, bro. I'm already out, bro. I mean, it has been 3 hours, like, mind you, like, fair enough, but like, it's not good enough. Like, it's not good enough. It's not good enough. Oh, I don't even know what study session is, because it technically is too. Oh yeah, bro, I forgot to change the freaking thing. Oh my god, bro. Oh wait, let me just change this. Yeah, that's more like it, cuz that's more like it. Bang. Yeah, I love the streaming stuff and that, but it's just too much effort, bro. It's genuinely, it's just too much effort. I wanted to finish this chapter and then move on to maths, but I might just have to move on to maths now because kind of like my brain is just not functioning, bro. My brain just feels like it's switched off, switched off a long time ago. Oh man. What, bro? What is this trolley, bro? Oh my god, bro! Give me my ticker tape because puts 50 dots per second in the ticker tape. Still like that, and then you have an. I know, man. Dude, do I have to go take another cold shower, bro? Bro, I think I might just take a break, bro, because right now brain is not braining. So yeah, I'll